to understand basic concepts as in lipid nanomaterials, inorganic materials, and ferromagnetic nanomaterials, and just try to give insights of how zero field NMR can be used in thin films as well, though qualitatively. Okay, let me start with what is known to us. What is known to us, we know electromagnetic radiation, which spans from 10 to the power of 4 hertz to 10 to the power of 22 hertz. And this entire electromagnetic spectrum, from physicist point of view, if you look at that, we have subdivided depending on the applications for a material scientist perspective into radio waves, microwaves, infrared rays, and visible light, where visible light is the one which enables us to see things around us, and ultraviolet rays, and X-rays, and gamma rays. And though this entire electromagnetic spectrum itself is the major tool to study for any of the characterization or sort of spectroscopic studies, we will narrow down our entire discussion in this presentation into some of the finer aspects. Now, let us try to understand why do we really worry about this entire electromagnetic spectrum. If you consider, as it is given here, if you start from a molecule and what are all the motions occurring within the system can be studied using this entire electromagnetic spectrum. To begin with, if I am talking about rotation of a molecule, then that whatever the energy is required for a molecule to rotate, that comes in the far infrared region of the electromagnetic spectrum. And again, if you come back to the vibrational spectrum, then that comes to the near infrared region of the electromagnetic spectrum. And then if you talk about the electronic transitions happening in the system, that electronic energy states, they come under UV visible region. And again, from spectroscopic point of view, we get into IR and Raman spectroscopy. Those things intentionally I would like to avoid it. And now we started from infrared rays and visible and ended with visible and ultraviolet rays. Now we will try to go back in the backwards from infrared, that lower frequency than that of infrared rays, where we will consider spin of a given material or a given constants of a material, where we identify that portion, that is this portion of the electromagnetic spectrum that we call it as radio waves or radio frequency and microwave frequency, where what we are considering is magnetic component associated with electrons and nucleons, how well they interact with electromagnetic radiation, that we are discussing in today's topic, that we call them, whenever the nuclear, in the sense magnetic property of the nucleons and magnetic property of the electrons, when they do interact with electromagnetic radiation, there's a resonance which happens, the corresponding energy level difference matches with that of the incident energy, electromagnetic radiation, that we call it as nuclear magnetic resonance and electron spin resonance. Okay, we'll talk about that in detail in a minute. And just for the completeness sake, whenever we come back to the right portion here, that X-rays, whenever we are having innermost electrons, whenever the transitions occur within the atom, innermost electrons, whenever the transition occur, then X-rays are produced. And whenever the rearrangement of nuclear particles, that is rearrangement within the nucleus, do happen, that give rise to that gamma rays. It is only for the completeness sake. Now we will narrow down our interactions or our entire session for this nuclear magnetic resonance. Now, let us try to understand what is this nuclear magnetic resonance. That is, in the short form, we call it as NMR. NMR, nuclear magnetic resonance. It is a spectroscopic technique which exploits the properties of the nucleus. And all of us are very well aware of the fact that nucleus consisting of protons and neutrons, and we know that protons do have charge, but neutrons do not have charge. They are neutral particles, but they possess this entire nucleus or nucleons together. Nucleons possess magnetic moments. What is the meaning of magnetic moment? It is all these nucleons behave like a tiny magnets. And we know that whenever we keep these kinds of tiny magnets, what is given in this left-hand side figure, and they are randomly distributed within the molecule. But at that point, if you start applying external magnetic field, the way this green arrow mark is shown, then what happens? These individual nucleons, they start revolving. Instead of calling it as revolving, we call them as they start precess around the direction of the external magnetic field with certain frequency. That frequency is directly proportional to the strength of the magnetic field. Here, when, just to read out the sentence what we have written here, when this tiny nuclear magnet kept in a magnetic field, it precesses at a particular frequency which is proportional to the magnetic field around the direction of the magnetic field due to the nuclear Zeeman effect. All of us have studied about Zeeman effect. Basically, NMR and ESR are subparts of the Zeeman effect, where the magnetic property of the given matter is interacting with the magnetic field. Okay, that we call it as nuclear Zeeman effect. Now what happened? We have got these individual nucleons, they start precessing around the direction of the static magnetic field with a particular frequency. During that time, whenever we apply electromagnetic radiation of same amount of frequency at which they are revolving around the static magnetic field, then that nucleus or nucleons, nucleons absorb energy from the radiation and they go to excited state. We will discuss about this from the quantum mechanical picture in a while. Then this nucleus absorbs energy, and because of that we get a signal that we call it as, the entire concept we call it as nuclear magnetic resonance. Now, if this is so, can we do, the obvious question is, can we do NMR of all nuclei, because all nuclei do contain protons and neutrons? Okay, let us try to answer, but before that, let us try to look at one more slide. For the continuity purpose, whatever we discussed in the previous slide, same thing we have represented here. This is only an experimental part, how we do. Usually, to apply external magnetic field, again, I will come back to this point, this magnetic field, to observe NMR signal, we need not to apply external magnetic field always. Okay, that will come to the later point. But what is known to most of us is that when we keep a given sample in this coil, that whatever the system like nanomaterial or bulk material or biological material, when you keep it in this particular coil where it is connected to the spectrometer, this entire probe, and at that point, if this sample is under the influence of external magnetic field, then they start precessing around the direction of the static magnetic field, making a cone. That's the same thing what we have written here. Zeeman effect, nuclear magnetic moment and static magnetic field, these two interact and give rise to an energy difference delta E. This individual energy level splits into the individual energy level splits into two energy levels. One is plus half and minus half, and that energy difference delta nu is given by h nu, where h is Planck's constant, nu is frequency, and that is directly proportional to the magnetic moment mu and strength of the external magnetic field B naught, and that in turn can be written in terms of gamma h by 2 pi into B naught, where gamma is the magnetogyric ratio, and this magnetogyric ratio purely depends on the particular nucleus what we are studying. Therefore, what I mean to say, whatever the systems we consider, up to this point relation is valid, but to exactly measure the energy difference, we need to consider what nucleus or what element we are doing NMR. For what element we are performing NMR experiment, and what should be the corresponding energy purely depends on this term magnetogyric ratio. And here, that's one of the bottom line of this slide. And here, spin whenever we are having two energy levels, and if we excite or if we shine electromagnetic radiation of right amount of energy or frequency, then this spin precesses around the static magnetic field along the z-axis, and NMR signal can be observed when electromagnetic radiation is pulsed to the x-axis at the Larmor frequency. Why did we use these technical terms? For simple reasons. This NMR, this transition, whatever we are considering, we can observe continuously or in a pulsed manner. Okay, we are not getting into details of that particular techniques. Okay, what the bottom line or take home message from this slide is that whenever we shine electromagnetic radiation to this energy level, absorption occurs. That absorption can be measured, and there are characteristic features of any spectrum. From those characteristics, we can get information about the material with which we are studying. What happens whenever this kind of absorption occurs? That sample coil can be written in this particular fashion. Whenever absorption occurs and they come back to ground state, while these excited atoms coming back to ground state, they do emit radiation, and that emission of that particular radiation, we call it as free induction decay, and this is what we observe in NMR signal. This we call it as NMR signal, and for practical purposes or wherever you have seen, you would have seen NMR signal in a different fashion. This is the time domain signal. If you do the Fourier transform, then this Fourier transform of this time domain signal gives you frequency domain signal. That is very much familiar to many of us. Okay, this is how the detection happens. What we do, we keep our system in the presence of magnetic field. When external radiation's energy matches with that of the energy difference between these two energy level, absorption occurs. That leads to emission of radiation of the same amount of energy. That we call it as NMR signal in time domain. Now, what do you mean by nuclear magnetic resonance? Because as most of us may be aware of, there are 6 to 7 Nobel Prizes are awarded based on or awarded to the scientists who contributed significantly to this nuclear magnetic resonance. This tells us that it is sort of a ocean. Therefore, let us try to understand how we classify this nuclear magnetic resonance into different parts. Okay, this nuclear magnetic resonance is subdivided into solution state NMR, solid state NMR, and what is popularly known to everybody is magnetic resonance imaging. Okay, and let us try to understand one by one. What is solution state NMR, solid state NMR, and MRI imaging? In solution state NMR, the aim of doing this solution state NMR is that to find out the structure of a given compound. And whenever we want to study the structure of a given compound, whenever we prepare a compound, that compound structure, if you want to analyze it, then we use certain terminologies called chemical shift. And usually this technique is used by chemists and biologists. Quite in the sense, only recently for some glass systems, even physicists also, they started using this chemical shift interpretation of the NMR spectrum. And when it comes to solid state NMR, whenever we want to understand the structure of a given molecule along with what is the dynamics, what are the motions which are occurring in the system. Then we go for solid state NMR. And how do we measure the properties, the dynamical property and structural properties of the system? We go with relaxation rates, and they are in turn related to the spectral density functions. And most of the physicists and recent days, even biologists are also have also started using this solid state NMR. And then when it comes to the hardcore application, or what is even layman is able to get the benefit out of this nuclear magnetic resonance, is due to magnetic resonance imaging. And just to give a brief view of this MRI is that our body consists of lot of water, where we consider water consisting of hydrogen. That hydrogen NMR, which with little more complex units or with little more complex concepts, we record image of a proton NMR or hydrogen NMR. That NMR or MRI is used to diagnose the disease. Please remember that MRI doesn't solve, it is not a curing technique. It only recognizes where is the problem. Okay, if you get time, we will touch upon that. And what do they use? They use some color contrasting agent just to manipulate this relaxation times when they record NMR spectrum of the human body or any other animal body. And this is mostly used by biologists. But all of you would have heard about this interdisciplinary or multidisciplinary research. In research, if you cannot really call yourself as a chemist or physicist or a biologist, therefore, what we are considering, if I want to study all these at a time, and if I am a material scientist or biophysical chemist, I need to concentrate more on the solid state NMR. Therefore, my entire talk will be concentrating more on this solid state NMR. And to answer to our previous question, can I do NMR of all nuclei? It appears that yes, we can do, because all these atoms do have protons and nucleons, but unfortunately no, because it depends on the nuclear spin. The nuclear spin is the total nuclear angular momentum quantum number, and it is characterized by I. But for certain nuclei, this spin quantum number I will be 0. And whenever we are having spin quantum number I is 0, okay, we cannot do NMR, because in our previous equation, when I becomes 0, whatever the mu factor we were considering, that also becomes 0, we cannot do. Therefore, only nuclei with spin quantum number I, which is not equal to 0, can give rise or can absorb electromagnetic radiation, giving rise to NMR signal. Examples what we have given here, a nucleus with even mass number and even charge, okay, that is atomic number basically. Then if we are having even and even, they give rise to C12, the C612, oxygen, carbon 612, oxygen 816. These, they do pair up with each other. And whenever they do pair up with each other, net magnetic moment will be 0. This we can understand using nuclear shell model. We will not spend much time over that. But whenever we consider a nucleus with even mass number and odd charge number, that is odd atomic number, that then they can be detected here. Okay, this is H2 is the deuterium nuclei. This is one of the isotope of the hydrogen. And boron 10 we can do. And this one also 714. This is boron 510. We can do that corresponding spin quantum number will be having integer value. Similarly, with odd mass number and odd charge number, that is proton 11. This is again carbon 13 is isotope of carbon 12. This carbon 13 is NMR active, and we can detect it, and they will be having odd integers. We will consider combination of all three varieties today for the discussion. Now, this is very first, or what we can say that up to this point, sorry, up to this point, all of us are aware of that, what is NMR. What we are trying to, in our lab, what we are trying to dwell more upon is that there is sort of an unconventional NMR. What do you mean by unconventional NMR? Let us try to learn about that, what is conventional NMR, where we apply external magnetic field to the system and we can perform NMR for all NMR active nuclei, and the corresponding mathematical notation of the NMR frequency is gamma times external, that is our Larmor frequency is directly proportional to the strength of the external magnetic field. Then whenever we are considering a compound which has these atoms, for example, hydrogen, carbon, phosphorus, then I can do NMR. Except for other technical reasons, I should be able to do NMR of all the compounds which are having these atoms. But there is one more unconventional, or there is another way of detecting NMR, that is through internal field NMR. In this internal field NMR, we no need to apply external magnetic field to the system or to observe NMR signal. We don't have to apply external magnetic field. For example, ferromagnetic systems, antiferromagnetic systems, where again same condition, same mathematical relation is valid here, but this, whatever the magnetic field we are applying, that magnetic field is generated at the site of the nucleus within these ferromagnetic systems. Okay. Therefore, to observe internal field NMR, I don't have to depend on external magnetic field. What are the nuclei for which we can do internal field NMR? They are iron, cobalt, manganese, nickel. We'll come back to these elements and certain examples in the later case. Bottom line of that one is we can also perform NMR in the absence of external magnetic field. Okay, and this is the general solution state NMR. Just to give you outline of that, what is solution state NMR. Please remember that I'm not going to spend much time on the solution state NMR. Here, this is basically whatever the pictorial representation I had shown earlier. We are using a superconducting magnet, and where we are inserting our sample, and sample one end wire is connected to the NMR console, and here NMR, in the sense signal induces, that will be amplified and recorded in the spectrum. This is the general schematic diagram of a NMR spectrometer. And in solution state NMR, people always talk about this chemical shift. Okay, this chemical shift, as we mentioned here, whenever we do whatever the free induction decay signal I shown in the previous slides, and if you do Fourier transform, that gives rise to peaks like this, absorption peaks per se. Then these peaks, we get independent peaks corresponding to the corresponding groups present within the given complex molecule. Okay, there is a trimethyl element, and there is a methyl element, okay, and there is an oxygen atom and carbon atom. Depending on this, if I perform NMR, then I get two different independent peaks that would help us to identify what are the functional groups present in a given molecule. That is represented in the form of chemical shift. Or just to give you that, the origin for chemical shift is how electron cloud is surrounded by the given hydrogen atom. For example, if I am performing hydrogen NMR, then what is the electron cloud present over there? Depending on that, the electron cloud shields number of atoms associated with that. Okay, and depending on that, we get different peaks. As I mentioned, that is represented by chemical shift. I will not really get into details here. Let us directly switch over to the solid state. Before that, why it is so important, that is, even if I consider a protein, a big molecule which is having 100 kilodalton, even then we are able to identify small functional groups present in the given compound. That's why physicists and chemists are heavily depending on the solution state NMR. Now, let us try to understand what are the concepts or what are the things people are studying using NMR as a spectroscopic tool. Where, as we are already aware of that, this is MRI image. In hospitals, we are doing it, and there is a functional imaging. This is for different purposes we are using it. And NMR or component of NMR is NQR that can be used for detecting explosives. And if you come back to the left-hand side, these are the things. And agriculture, we are using it. In soil science, we are using it. In physics, we can use this nuclear magnetic resonance. In forensic science, and as I already mentioned about the structural chemistry and structural biology, like this kind of a complex NMR spectrum, we can get it by recording the spectrum. By analyzing the spectrum, we can get this structure of a protein embedded within the system. These are conventional ways, and here what we are considering in my talk, I am concentrating on the material science aspect of this NMR and what are the physics, what are the different motions which can occur within the molecule, what are the time scales occurring within the molecule. Those are my highlights, or what are the fundamental properties what I am discussing today. These three pictures, 1, 2, 3, these are our, in the sense, these are the concepts what I am concentrating right now. Now, again, right now we introduce electromagnetic spectrum and we introduce NMR spectroscopy also, and we talked about this solid state NMR also. That solid state NMR, as I mentioned, that it is nothing different. Our systems will be in the solid form or in the sort of a gel form. Okay, that only the system is there is an analogous system with respect to the solution state, and whenever we talk about dynamics happening in the system, that broadly, I might be oversimplifying it, that broadly we call it as solid state NMR. And again, within this solid state NMR, I will be concentrating on 3 set of systems. The first system is lipid nanomembranes or lipid nanomaterials, and how we can apply solid state NMR to lipid nanomaterials and to understand membrane proteins. Okay, and they are internally connected to the mechanosensitive channels associated in the body. Okay, how do they work? That is our first talk. And the second part, we are trying to talk about that it's not really nanomaterial. So like in bulk material also, how physical concepts like phase transitions, whatever the activation energies corresponding to particular groups and quantum rotation tunneling happening in the system, that we are going to study in the second part of the talk. In the third part, we are talking about internal field, what I explained earlier. Okay, now, what is a cellular membrane? How does it look? All of us know that cellular membrane, they are consisting of lipid bilayers, and these lipid bilayers are impermeable to ions and polar molecules. And the basic purpose of this cellular membrane is to make compartments within the cell. Okay. Within a body, how these internal compartments are done, that compartments or walls are made up of lipid membranes. And usually these lipid membranes, as you can see that there is a thread-like structure that can be represented in the fashion, or they are actually consisting of these many carbonyl chains, as is mentioned in the left-hand side of the slide, where there are different groups possible. We'll come back to this point in the next slide. And they are attached in such a fashion that, okay, the top portion, what we are calling it as, we usually label it as head group, and this lengthy thread-like structure, we call it as chain. And these head group are where we have more number of atoms are joining together. At that portion, these head groups are water friendly and they attract water. And at this point, at the center point, they hate water. Therefore, only heads come together and tails come together. And they join back to back. Therefore, we call it as bilayer membrane, lipid bilayer. There are two layers, as you can see here. Okay, there are two layers joined together. This is hydrophilic nature and this is hydrophobic nature. And because of the hydrophobicity present within the lipid molecule, they form a bilayer structure. And these bilayers are always associated with proteins. In the sense, proteins are generally categorized as membrane proteins and transmembrane proteins are proteins which are present within the cell membrane, within the cell or outside the cell, or some proteins are passing through the membrane. Therefore, if I want to understand how these membrane proteins, and all of us are very much aware of the fact that why we need to study about membrane proteins. We know that all drug industry, pharmaceutical industry is purely depending on how well drug is delivered to that protein, which enables us to cure from a particular disease. Therefore, if my major aim is to understand how protein works, obviously, since it is embedded within this membrane fabric, I need to understand how this fabric would affect as a function of some other parameters, and then how these membrane properties are correlated or associated with the protein properties. The combination is always essential for us to come to a logical conclusion or for many of the advantages. Therefore, here proteins mediate distinct cellular functions, we know that, and the role of lipid-protein interactions in biological mechanisms is essential for us to understand how proteins get affected in the presence of external forces. That could be any osmosis process, or that could be pressure, or that could be temperature. The best example for this entire, whatever the picture I have shown, is your skin and hairs. Your skin is a bilayer membrane, your hair is a membrane protein. For example, whenever you take your hand near to the hot object, what happens? You can see that straightening of the hairs. How do they respond? Then they do respond because this external heat does rearrange certain arrangements in the lipid molecules, that is your skin, and that makes your hairs to go straight or make them straight. Okay, that is one of the better examples just to correlate with our regular activities. Therefore, there is much more, and there is another concept called mechanosensitive channels. For example, if some ions have to come out of the system, for example, I might be oversimplifying it. Whenever sweat is coming out of that, how does some of the sugar which is present inside your body is coming out during the atmosphere? Whenever we get tired or if you run fast, how does sweat come out? Therefore, that sweat has to come out. That I might be oversimplifying it here, that we call it as, in technical terms, mechanosensitive channel. Whenever there is a tension created in this lipid structure, then there is an opening happens within the system, that we call it as mechanosensitive channel. They do get activated, and some of the ions do pass through this membrane whenever certain changes happens. Therefore, to understand all those concepts, our fundamental issue here is to understand how do these lipids behave in the presence of external forces. Okay, now let us try to consider what are the other constituents we might be having for these lipids. Usually these lipids are subdivided, as we can see, that different head group moieties and varying hydrocarbon chain length. Depending on the chain length and depending on the unsaturation, what this red arrows we have given here, this is unsaturation, we do have double bands. Then we give different names for different lipids. And also, depending on what is the head group present here. Here, methylene group is present here only. NH3 group is present. Therefore, depending on these things, just to give an example, this is dimyristyl phosphocholine. Okay, this phosphocholine, whenever phosphoethylene happens, that CH3 group comes into picture. And DPPC, this is dimyristyl. And whenever we are having oleic acid or myristyl group, then we call it as DMPC. Most of the studies what I am going to discuss today are basically we have taken DMPC as a model membrane and we studied certain properties. But in nature or whatever the biological system, we will be having combination of all these three types of lipids, and also all of us are aware of this cholesterol. Cholesterol is also integral part of the bilayer membrane. Therefore, why I have used another term called elasticity, we will come to know after 2-3 slides. Okay. Therefore, if I want to study, we need to our biological system consisting of all types of lipids. Either it is saturated lipid, unsaturated lipid with different head groups, and all these components do play major role. Okay, and here this entire carbon chain we are labeled into for DMPC. It is consisting of 14 carbonyl chains. Okay, therefore, please remember this term also. We have to use it in the next slide. Now, along with this structure, okay, these lipids, whenever we make them assembled together, then there are different types of motions can occur within this system. In the sense, what I mean to say, within this system, 1 minute. Okay. Within this lipid assembly, they can undergo different types of motions. One is whatever we have written, principal axis to intermediate frame. If I consider only 2 bonds here, okay, motions can occur at that point also. These CH2 groups, wherever we are considering, another C is carbon is attached to, should be attached to 4 hydrogens, right? 1 hydrogen, instead of 1 hydrogen, 1 carbon is attached. Here, another carbon is attached. Therefore, there are 2 more hydrogens which are empty. That we call it as methylene groups. Okay, CH2 groups. And those 2 CH2 groups, how they start vibrating or rotating, that we call it as segmental motions. That segmental motions, their time scale will be in the order of 10 to the power of minus 12 seconds. In the similar fashion, we consider one entire chain, okay, one particular nuclei, and we draw one more line at the center, and how well this orientation or the way it is given, the arrow mark here, this molecular diffusion, that molecule diffuses within certain boundary, those motions will be those motions happen in the time scale of 10 to the power of minus 9 to 10 to the power of minus 6 seconds. That is approximately microseconds to nanoseconds. And there is this entire assembly of lipids, they do undergo sort of undulations or deformations. Those deformation, this entire loop is changing. It is like a thread. Entire thread, if I can always make that entire thread to move around, those we represent it as viscoelastic membrane deformation. They do, in the sense, the corresponding time scale will be in the order of 10 to the power of minus 3 seconds. Therefore, to understand all these, in the sense, as you might be wondering that the time scale or motions occurring within this lipid membrane systems vary from one end to the other one, from 1 second to 10 to the power of minus 12 seconds. Therefore, if I want to understand all these motions, we need to rely on many other experimental techniques as it is given here. For picoseconds, we go for inelastic neutron scattering and IR and Raman spectroscopy. This we have already know about that. And if you want to understand this molecular diffusion, we go with nuclear spin lattice relaxation and line shape, and we use ESR technique, or ESR technique is also called as electron paramagnetic resonance also. And then if you want to understand this molecular deformation, then we go for this transverse relaxation dispersion. Please remember here, these two are, there are two types of relaxations we are talking about within NMR. One is spin lattice relaxation, other one is spin relaxation. That spin relaxation, we call it as transverse relaxation. Spin lattice relaxation is called as T1 and this is T2. We'll come back to that point. The beauty of this one is I have not paid much attention to this simulation work with which people study these motions extensively. We'll come back to that later. Therefore, within NMR, we will be able to measure these two techniques. And you might be always wondering that what is the major advantage of solid state NMR, where we are also getting structure, and in X-ray also people are using X-ray extensively for their material characterization. The beauty of this NMR here is that X-ray is like a static camera or where we get still photograph. But NMR, along with still photography, it acts like a video camera or motion picture. Where, for example, the fundamental example what I give always is that if you take a photo, you will only see my position at that particular instant of time. For example, and the contrary, if you do NMR spectra and if you perform relaxation time measurements, along with my static picture, when I am speaking as of now, along with my static picture, you would see how my hands are moving and what is the motion at which I am moving my hands, how well and what is the time scale at which my lips are moving whenever I am speaking. All these kinds of minute information one can extract from NMR if you just compare that X-ray. It doesn't mean that it is superior over other technique. Okay, some of the things what X-ray can do, NMR may not be doing, but it gives both structural information as well as dynamical information of a given system is my bottom line. Okay, and okay, along with this, 1 minute please. Okay. Oh, okay. Thank you. And here now let us, for biological systems, let us try to understand what I have presented in this slide. Okay, it looks little complicated. Please give me 1 or 2 minutes. I will try to dig it out one after the other. What we are doing it, for example, if I want to do NMR of this entire lipid, what I have shown in the left-hand side, what would happen? I will get NMR signal for hydrogen present throughout the material. I think all of you are able, you are able to see that, okay, entire big molecule contains hydrogens at every corner here. Every functional group has hydrogen. Then if I want to measure NMR spectrum, then I get signal, NMR signal from every point, and my spectrum will be much more complicated. To avoid these complications, what we do, we selectively deuterate CH2 group at one particular point at a time or all together, and instead of hydrogen, we keep deuterium. And please remember, hydrogen, the spin quantum number for hydrogen, if I forgot to mention or highlight that, hydrogen 1H1, that is hydrogen has spin quantum number of, and deuterium, since it has even mass and odd atomic number, its spin quantum number is 1. Therefore, in the presence, initially there is no difference, and in the presence of external magnetic field, one energy level splits into 3 energy level, and that is because of the Zeeman interaction. But we have to consider whenever we are having a spin quantum number which is more than 1, there is a quadrupole moment comes into picture along with the Zeeman interaction. That quadrupole interaction again slightly moves these energy levels into different energy levels as it is given here. The details we are intentionally avoiding at this point. Okay, and therefore what we get, the bottom line here is, if I measure the deuterium NMR of a particular lipid system, I get two peaks. One is having slightly higher energy level with respect to the Zeeman interaction. Other one is having slightly lower interaction. Okay, therefore we do get two peaks. Now we'll try to understand right hand side picture. What we are doing is, this hydrogen in the carbon CH2 group, what I am doing is, I am replacing hydrogen with the deuterium, and what I am, by measuring deuterium NMR spectroscopy, I am connecting all the motions which can occur at the CH2 group with respect to the laboratory frame. I am correlating with respect to the functions here, and this is Legendre polynomials we will consider. But the bottom line of this entire slide is, okay, by measuring, whenever I told you, I get two NMR signals. These two NMR signals, the separation between those two peaks give rise to delta nu q. Again, I am going to show the spectrum and we will understand it in a better way. Just to come for the completeness sake, I am considering the difference between two peaks, what we get from this deuterium NMR is related to the angle at which it makes this carbon deuterium bond makes with respect to laboratory frame is comprising of all these motions. Okay, we use group theory here. We can always decompose these motions independently, or we can write that entire, this is L represents in the bottom, L represents laboratory frame, and P represents principal axis system for a carbon deuterium bond here. This entire motion we can measure as a function of delta nu q, and that is related to one parameter SCD. We will talk about it in the next slide. I hope here the bottom line is, because our entire molecule consisting of large number of hydrogens, we want to make measurements only for a particular segment. With even by measuring NMR signal at a particular segment, we can connect that properties with respect to the entire bulk nature of the given molecule. Now, that is the bottom line, what we are trying to do that, and within that, what is our main objective here in this particular topic is, our interest was to identify whether in the presence of external pressure or temperature, whether this membrane, whether they do these membranes, whether they deform or not, because there was a lot of ambiguity with respect to the deformation of a molecule in the presence of external force, especially pressure. That we wanted to highlight and we wanted to understand, and also we wanted to understand what are the different regimes of intramembrane forces which can happen. This is basically, our system is biological in nature, but whatever the problems we are addressing is of physics. Okay, and we use this solid state NMR technique here, and this is the overview of that entire subsection, what I am talking about that. And we connected the results, what we obtained from solid state NMR with respect to the protrusions and undulations which can occur within the system. Okay, now this, let us try to make unit structure or crystal structure of the lipid systems what we are considering. This is the lipid head group and this is the chain, and this the combination at the top end, because these are all hydrophobic in nature, and we get these water molecules present next to the head groups in the same fashion at the bottom. At the center, number of water molecules are very, very less. And this, the distance between from top end to the bottom end, we call it as D, that is the interlamellar spacing. It is basically these kinds of unit cells are packing one on top of each other. It is very much similar to our basic crystallography. Okay, and this there are terminologies. What we have given is hydrocarbon thickness, DC, the thickness from this bottom end of this end to the other end of the head groups of the other layer, and DW is the water interlamellar water spacing, this whatever the water present in this material. And head group thickness, as it is obvious, this purple color round group is the head group, and NWL is number of waters per lipid. Okay, and why I am talking about this, what are the parameters on this NMR one can study is that by measuring this hydrocarbon thickness, and I can measure how this cross-sectional area of individual lipid, I can calculate cross-sectional area per lipid by making NMR measurements. Same thing can be studied using X-ray also. Small angle X-ray scattering method also we can use this cross-sectional area. And our final aim is to identify or to measure this cross-sectional area. Does it change with respect to temperature or pressure is my major goal. Okay, therefore we have defined what is cross-sectional area and what is hydrocarbon thickness. And this has been discussed explicitly with about 40 pages of detailed review. If you are interested, you can please go through this review. And now we will come back to the original picture, NMR's picture, where we discussed earlier that each deuterium NMR or each nuclei in the carbonyl chain will give you two signals. That you can see that, for example, if I consider carbon 14 or carbon 2 to 3, these one peak corresponding to carbon chain 2, 3, 4, this is one peak, the corresponding, the associated another peak is at the right hand side. The distance between these two is our experimental observable. Please remember that though I am considering this entire lipid assembly, it is like a bulk material. By making solid state NMR, deuterium NMR spectroscopy, in the sense spectroscopic signal, I can get minute details corresponding to individual atoms present in the entire molecule. Though I am taking a macro sample, even microscopic observables one can detect using solid state deuterium NMR. Okay, that is the beauty of this deuterium solid state NMR. Because what I have done it here is, instead of deuterating only one position, I have deuterated this entire chain, both this side, this chain, as well as this chain. Okay, together, that's why I am getting two sets of signals. In the sense, whatever the signals we are getting, same notation we can apply here also. Now, as you can see that methyl group, that 14th chain, the distance between these two peaks is very, very less. But at this point, the distance between these two groups is very large. Let us try to understand what we can get out of this by measuring the distance between these two peaks, that we call it as quadrupolar splittings. Okay, this deuterium NMR provides residual quadrupolar coupling constants. And once we have this, once we record this NMR spectrum, we analyze this data by calculating area under each curve. And once we know what is the area under each curve, then we assign how many atoms might be contributing to one signal. And once this assignment of atoms for individual peak is done, then what we do is, as we discussed earlier, this is the delta nu q, quadrupolar coupling constant, quadrupolar splitting. That quadrupolar splitting is related to the angle subtended by that particular principal axis system, or that one particular carbon deuterium bond with respect to laboratory frame. And once we know this delta nu q, and delta nu q would vary from one molecule which is close to the head group to the terminal methyl group. As we can see, the delta nu q is not constant. But experimentally, what is important, there is a dedicated theory associated with that, which tells us that what we need to understand is only to pay attention toward this, what is the plateau region of quadrupolar splittings here. That is the peaks corresponding to first few carbonyl groups, that is sufficient for us to get experimentally detectable property of a given system. Then what we are doing now, we are measuring delta nu q, And that delta nu q is residual quadrupolar couplings enable us to calculate carbon deuterium bond order parameter. The experimental parameter from deuterium NMR is carbon deuterium bond parameter, and that is represented by SCD, carbon deuterium bond order parameter, that is given by delta nu q, that is what the experimental observable, and from that, and this is the coupling constant, it is known for this carbon deuterium bond. From this, our experimental observable is SCD, or what we call it as bond order parameter. In simple sense, we call it as order parameter. And once this order parameter is calculated, this order parameter would help us to calculate the cross-sectional area of a given per lipid and what is the bilayer thickness. Basically, what I am deriving at the end of this particular slide is that by measuring the quadrupolar splittings, I can measure the area, cross-sectional area per lipid and bilayer thickness of a given whatever the lattice we have considered, hypothetical lattice we had considered. Therefore, now our job is, we know that how to record the NMR spectrum and how to correlate that experimental observable with respect to the material property. Now we will play around with the different conditions. Okay, what we did in our measurements, one of our set of measurements, we wanted to apply extra pressure to this membrane system. There are two types of, there are a couple of ways of applying pressure to the system. I have neglected many of the slides here. Here what we did, we took polyethylene glycol and we started adding this polyethylene glycol system to the lipid water system. Then what happens, this polyethylene glycol, these start applying osmotic pressure to the given membrane system. Basically, what this osmolyte is doing, it is trying to take out water present within the membrane, within the lipid water mixture. And that is one way of applying osmotic pressure to the system. Second one is, what I did, I added sufficient number of atoms, sufficient number of waters with respect to lipids, and then I kept on taking out number of waters present within the system. Therefore, I am dehydrating the given lipid water system. Then, as you can see that with the 58% lipid and water, the quadrupolar splittings were very small. But when we started decreasing, or when we started taking out amount of water molecules present, when that water percentage, when I decreased to 3.1 as it is given here, then you can see that there is a substantial change in the splitting between these two peaks. Okay, the same thing happened when I started adding more amount of polyethylene glycol system to this lipid water system, where we had 50% of water and 50% of lipids. And when we started adding more lipids, then these lipids started absorbing or taking out amount of water from the lipid water system. Then when we recorded NMR spectrum, we could see that there is a substantial change in the spectra. Okay, this is characterized or interpreted in terms of carbon deuterium bond order parameter. We can see that as we kept on, this is 58%, when we kept on decreasing the amount of water to 3.1%, this bond order parameter increased drastically. Same thing happened with respect to increase of weight percentage of polyethylene glycol. This, what is schematically, if I want to do that, whenever, if you consider this yellow thread-like structures as these thread-like structures, if I consider them as polyethylene glycols, these polyethylene glycols are removing waters from this intermembrane system. And this one, as you can see that it looks like a half-cut onion. Okay, there are onion rings. Intermediate between these two onion rings, large number of water molecules are there. And if I dip this this onion in a bucket of water, where I apply some more stones within this bucket of water also. Then sort of the stones, assume that hypothetical example I am giving, then these stones start pushing away water molecules present between these two onion rings. That is given by this thread-like structure is our polyethylene glycol. They drag water molecules from intermediate layers to the bulk water positions. Therefore, while doing that, opposite pressure is created on this bilayer that makes this thickness and area per lipid to modulate or to change. Then what happens? The transfer of water from interlamellar space to the bulk water phase induces atmospheric pressure, osmotic pressure on the membrane. Then whenever this osmotic pressure is created, that creates extra pressure that modulates or that gives out different NMR signal due to thickening of the membrane. That is basically what I am driving here is this thickness of this bilayer starts increasing when more osmotic pressure is applied on the system. And now let us try to understand same thing with respect to osmotic pressure. So this is the same picture as I mentioned that I am reiterating once again here. This can be understood in similar to that of cut onion, and water molecules are moving away, thereby creating extra osmotic pressure. And if I quantify how much pressure I am applying to the system, then if I plot pressure along the y-axis, and we already discussed that we can measure area of cross section of the given lipid, and if I plot it as a function of pressure, then we get these kinds of pictures. Please remember that this is hydrostatic pressure. This yellow symbols, this was reported by some other technique, not from our group. Okay, they assume that, or they came to the conclusion that though they applied osmotic pressure up to 140 megapascal, okay, or we can say that our room temperature atmospheric pressure is 1 atmosphere, they went up to 1400 atmospheric pressure, then they saw marginal variation in the cross-sectional area. At that point, what did they do? They kept on applying a piston type of pressure to the system, hydrostatic pressure. But when we measured cross-sectional area, or when we applied pressure to the given system, both dehydration pressure as well as osmotic pressure. Please remember that dehydration pressure is, I just kept on decreasing, or manually I kept on taking water away from the system. Osmotic pressure is, for a given system, I kept on adding extra osmolite. So that since osmolites behave like particles, they start, this is the colligative property of the osmolite, they start extracting more water away because of the osmosis. Okay, and then in our measurement, we saw approximately 20% variation in the cross-sectional area, though we applied osmotic pressure up to 20 megapascal. And you might ask that, okay, what is the big deal about that? How does it really affect, or what information as a physicist one can get out of that? If I draw a line here, and if I measure the slope of this, the way data points, though I have used only 3 data points or 4 data points here, this is a representative graph, what we are having it. Okay, we had about 10 to 15 data points here. And if I draw this slope, and if I draw the line and measure the slope of this curve, I get the elastic property. What is the modulus of elasticity for given particular lipid here? And that modulus, whatever the rigidity, what is the modulus we get here, that modulus is correlated with respect to mechanosensitive property of the given membrane system. Okay, that is the physics part of that. One of the physics properties one can measure. It is by, though our system is biological system, we are getting material properties of the components of the lipid membranes. Okay, and also another point what we wanted to, or what we shown about 10 years ago or about 8 to 10 years ago, is that we were able to show that membranes do deform in the presence of external pressure. And the second point what we shown in this, along with this, while measuring this cross-sectional area, we started calculating osmotic coefficient. Okay, how much osmotic coefficient could change as a function of when we start removing the water. That layer, whenever we remove water, more osmotic pressure is created on the system. Based on those calculations, details are not given here. We can study that ondulation do happen within the system, and the protrusions also dominate. Like whenever we consider two atoms here, this is basically the opposite picture what I have shown from left hand side to the right hand side bottom. This ondulation is that this entire thing is, this is one bilayer and this is another bilayer. It is also same thing that this bilayer corresponding to the top, this head group corresponding to the top bilayer, and this bottom head group corresponding to the bottom bilayer. And these two, how well they are packed. This is between one layer of the onion ring, and this is the another layer of the onion ring what we are considering. Then how well these head groups can protrude in the within the close assembly of another set of head groups. That protrusion forces we could observe only whenever we kept on decreasing the amount of water to lowest level. That 3.1% we shown that these forces dominate. And whenever we have more number of water molecules, ondulation forces dominate over there. These things are explicitly explained in this particular publication. And similar type of measurements, we did it with respect to the cholesterol, and we took another lipid molecules, and this we are trying to understand that how cholesterol can modulate the properties of the lipids and how well it would enable us for all biological applications. Okay, and the second part is, as we know that the spectral density, most physicists, we do know that spectral densities vary. Okay, depending on that, if I want to measure the spectral density, if my Larmor frequency and the correlation time, if they are almost equal or greater than 1, what would happen, how spectral density function look like. And by making measurements like from spin lattice relaxation measurements of the deuterium signal or any NMR spectrum, we can measure, we can correlate spin lattice relaxation times of the system with respect to the spectral density. And it is only whatever the picture I had shown earlier, by varying certain modification in the way we collect the NMR spectrum, we can flip this entire spectrum from negative magnetization to the positive magnetization, which enables us to measure the spin lattice relaxation time. Basically, in very simplified way, in the very first, in the beginning, we showed two energy levels. The spin lattice relaxation time is almost equivalent to say that how much time these atoms take to, once we disturb the equilibrium, how much time they take to come back to lower energy level is given by spin lattice relaxation time. Again, why we are using lattice, depending on the host where our atoms are present, this spin lattice relaxation time would vary. But along with that, this spin lattice relaxation time also varies as a function of frequency. Okay, we can measure spin lattice relaxation time as a function of frequency. For example, as we shown in the very beginning, the energy difference between two levels can be changed as a function of strength of the external magnetic field. If I keep on changing the magnetic field strength, then I can measure NMR of the same system as a function of different frequencies. And if I do that kind of an experiment, and if I plot it in this particular fashion, it follows a square law. This square law approach is very well established in our liquid crystal theory. I just want to bring it out. Though our systems are biological in nature, these are all connected to our physics problems. Okay, and these are the particular details. And same thing can be applied with respect to what happens to the system when we apply cholesterol to the lipid system. And if you apply detergent to the lipid system, whenever we apply detergent, that is C12E8, then membrane becomes thin. Instead of making it big, it becomes thin. And if I apply cholesterol, the thickness of the onion ring increases. Individual rings that would increase in the presence of cholesterol, that would decrease in the presence of detergent. That is the bottom line of this particular plot. Okay, and basically in this first particular topic, we discussed about this, what are the applications of this NMR and which could help us to understand ondulations and protrusion forces happening in the system. And we have shown that there is a remarkable change in the cross-sectional area per lipid. And we can, as I mentioned earlier, we can also measure the energetics of the area deformation that comes about 142 millijoule per meter square is the elastic property or modulus, in the sense quantification of energetics of the deformation can be measured with this parameter. Now we will get into a little bit of inorganic metal halides, how solid state NMR can be applied. And here I have taken two examples. Okay, one is trimethyl ammonium germanium chloride, and this is tetramethyl ammonium hexafluorophosphate. Okay, this is a perovskite material. Okay, and there are more applications for this hexafluorophosphate. And what is the major intention here is multi-nuclear solid state NMR studies. They provide information about the understanding of the molecular structure, dynamics, phase transitions occurring in the system, how conductivity mechanism is occurring in the system. All these things would enable us to fabricate new technologically important inorganic solids as the thrust area. Okay, and here just to have that, if I plot, and I have taken trimethyl ammonium germanium chloride, and we have made measurements of spin lattice relaxation time measurements as a function of temperature. Please remember here we varied temperature from around 400 Kelvin to 4 Kelvin or 5 Kelvin. And we observed that when we made this measurement, and if I extrapolate or if I expand only this high temperature region of the spectrum, I could immediately see there is a slope change within this first slope. And wherever there is a slope change, that to cross check that whether they are genuine phase change, there is a genuine slope change, we perform DSC measurements and differential scanning calorimetry measurement, and through that studies we observed phase transitions at the same temperatures where we correlated. What I mean to say is that these phase transitions can be easily or can be measured effectively using solid state NMR technique is one of the take home message here. And other one is at the low temperature quantum rotational tunneling can also be measured here using this solid state NMR technique, and whatever the motions or whatever the minima we are seeing it here, okay, they corresponding to one minima corresponding to methyl group, only CH3 group, other minimum corresponding to this trimethylene group. Okay, therefore two minima we could measure, and by measuring this minima and by fitting to the Arrhenius relation, I can calculate what is the activation energy corresponding to the motion occurring within that CH3 group. Again, this activation energy is the energy required for that methylene group to reorient from one equivalent configuration to the other equivalent configuration. And another example we took it was tetramethyl ammonium hexafluorophosphate, where please remember that I can do NMR of hydrogen, phosphorus and fluorine. And in this particular case, what I have shown, only phosphorus NMR was done by some other scientist, and for fluorine and hydrogen we perform the experiment. And here, just to understand some more detailed study, we perform this fluorine NMR and hydrogen NMR, solid state NMR at different frequencies, and which enabled us to distinguish what are the contributions due to hydrogen bonding happening with the system, and how hydrogen is influencing the relaxation of the proton and vice versa. Therefore, there are two in tetramethyl ammonium ion, the two types of motions can happen. One is within this cation, CS3 4 times, and anion motion also P of 6. These two orientations are possible. They give rise to their own minima. Okay, therefore, whenever we observe minima, at that point, if you fit it to particular mathematical expression or theory, proposed theory, we can estimate what is the energy required for this reorientation to occur. Okay, and as you can see that entire relation is much more complicated here. Just for the completeness sake, I have given there are different part components which contribute to understand it better. And then let me switch over to, I think, how much more time I am having? Another 20 minutes or 30 minutes now? Organizers?
Hello, sir.
How much extra time I am having?
Sir, still half an hour.
Half an hour. Okay, thank you. Okay, now we will move on to the third topic, where internal field or zero field NMR. Okay, this all of us are aware of this magnetic ordering, how it happens and how these systems are categorized, like ferromagnetic systems, antiferromagnetic systems, ferrimagnetic systems, and paramagnetic systems. Okay, and the corresponding examples are also given below. TC spins are aligned parallel to the magnetic domain. We call them as ferromagnetic systems. And whenever below transition temperature spins are aligned anti-parallel, that we call it as antiferromagnetic system. And vice versa, what the explanation is given. All of us are aware of these Curie temperatures and Néel temperature, above which how do they behave. Okay, now we will take some of the magnetic systems. Let us explore, can we make any useful solid state NMR measurements in these systems also. Here, basically, now I am coming to that nano systems explicitly. Okay, and why do we really care about this NMR and how well they would be useful for thin films and spintronics? I hope Professor Anil Kumar, he has mastery in this spintronics, and I just want to give a very little connection with respect to NMR, how we can use it in spintronic system also. It is a control of structure properties relation, starts with the knowledge of crystal structure. This is very general introduction, and to understand anything, first we need to understand the characterization. We have to characterize the given material, and we have to connect that structure with respect to magnetic and electronic properties of the system, and this spintronics, which combines both the use of both charge and the spin of electrons as information carriers, and that gives rise very good information. My bottom line in this slide here is this NMR spectroscopy provides an indirect tool to measure the density of states of spin polarized materials, and this has been extensively discussed in this one of these papers. It's a review. It is very well written review. We can go ahead that with this motivation. Okay, we'll try to move on to the next topic, and the schematic representation of one of the graphs. What they have plotted over here is they have measured internal field NMR, that is spin echo intensity. Okay, as a function of thickness of the film, what they grew in this spintronics, using spintronics technique. Okay, and whenever they measured, it is only for inspiration purpose. Okay, what they observed is that they were able to identify from this NMR spectrum, they were able to identify different crystal structures which are coexisting in this cobalt thin films using molecular beam epitaxy. Okay, in the sense, the bottom line will let us get inspired by looking at this graph. Okay, how well they are able to identify whenever they kept on changing the amount of coating also when they make different thickness of the thin film, they were able to identify how many layers are formed using this NMR technique also. With that inspiration, let us jump on to the systems what we personally studied. As we discussed earlier, I'll try to give some theory corresponding to this zero field NMR. The bottom line here is, for zero field NMR, I don't need external field. Even the field which is generated within the sample is sufficient for us to perform NMR spectrometer, the NMR signal, or to make NMR experiments. Okay, and our next few slides will try to understand what is this H internal, how do they arise. Okay, the origin of magnetism in the magnetic materials can be described as given here. The internal field, whatever the internal field, is an effective sum of the following terms. Let us consider here, whatever the field, internal field in this case, is that field seen by the given nuclei. It consists of, one is, for the completeness sake, we'll consider local magnetic field. Okay, whatever the local magnetic field seen by the nucleus, and also hyperfine field. Okay, effective hyperfine field due to the effective magnetic field due to the hyperfine field. Again, it is much more terms are involved here. Okay, what I mean to say here is that this internal field consisting of local magnetic field as well as hyperfine field. Again, this local magnetic field is subdivided into some other components. Let us not really worry, or not, we have to worry, but let us not pay much attention in this talk for the finer details of that. Let us try to understand what are the possible mechanisms which cause local magnetic field to arise at the site of the interested nuclei, where He is the external magnetic field if we apply. Okay, please remember that He, we are not doing anything in the zero field NMR, but certain groups along with that, within the along in the absence of external magnetic field, they do apply external magnetic field just to see some special properties. Just for the completeness sake, I have given He is external magnetic field, and HD is the demagnetization field, and H Lorentz is the Lorentz field, and H dash is the residual Lorentz field due to the non-cubic symmetry. We'll come back to these individual terms in the next slide. And this H hyperfine field consisting of dipolar field, orbital field, and FC. And again, this FC consisting of H core, H conduction electrons, and transfer. Again, I am not spelling out more, just for the completeness sake, I will talk about it. And then when we discuss again in the next slide, we'll talk about in detail about the function of individual terms shown in this slide. Now, my job here is, based on these different fields, okay, we can estimate the contribution from all these fields, create a net magnetic field at the site of iron is about 33 Tesla. The sense you, all of us are known that even 33 Tesla, continuous 33 Tesla is hard to achieve even today. Okay, all our magnets, whatever the commercial magnets in Indians of Science or major institutions across the country, we go up to about 27 or 25 Tesla is the external magnetic field what we have created. As you have seen in the second slide where I showed the schematic of the NMR spectrometer, the typical magnetic field what we apply externally is around 20 to 25 Tesla. But just the internal structure of the molecule itself can create about 33 Tesla at the iron site. Similarly, whenever we are having a cobalt nuclei in the given system, at that point, these, whatever the terms we have given in the slide, they contribute to 21 Tesla of the external magnetic field. And at the nickel site, we get about 6.5 Tesla. Therefore, the field generated at the site of these nuclei is not a small number, is my what I am trying to that is my bottom line, what I am trying to explain over here. Okay, 1 minute, please. Okay, now we will try to understand how does this IFNMR really help us identifying this. This is the summary of that what I am going to talk now. This crystallographic phases like phase centric, FCC, BCC and HCP for a cobalt sample can be able to distinguish from this hyperfine cells whether these crystallizations, if whenever we prepare a cobalt, when we synthesize cobalt, it's a pure element, then if they form different crystal structures, can our internal field NMR distinguish these types of structures is our first problem, what we are interested. And when we make thin film, okay, how well these NMR measurements can be used to characterize the interfaces and roughness of the interface and topology and concentration profile, can we measure it, is second topic. And the third one is, can we measure temperature dependence of spin lattice relaxation time as another tool to measure the spin polarization, and how well this, whenever we dope some other element to the system, how well it can affect the crystal structure or any other material properties. Now, as we discussed earlier, same thing we will consider here. The effective magnetic field seen by the nucleus is consisting of H effective equals H applied, dipolar and hyperfine field. And in ferromagnetic materials, internal field generated due to magnetization due to different origin is sufficient to observe NMR. This is basically the example what we have already explained here. Okay, and here this applied field is 0 now. What we are left with is H effective magnetic field seen by the nucleus consisting of applied field, dipolar field and hyperfine field. Since we are not applying any external field, let us neglect about this applied field. Let us concentrate on dipolar field. And this dipolar field again consisting of demagnetized field which cancels out in multi-domain particles. Let us come back to this. What do you mean by domain? And this, because whenever we make certain systems, domains are formed in these ferromagnetic systems where it plays a role in single domain nano samples where this demagnetization field is cancelling out in multi-domain particles. And the second term, Lorentz field, is related to saturation value of the electron magnetization. And local field, what we have given here is, which is arising from moments in Lorentz sphere except the central moment. Let us come back to this point once again. Here, this in ferromagnetic materials, the most important contribution from hyperfine interaction, that is between the nuclear magnetic moment and the spin orbital currents due to surrounding electron. Please pay attention here is hyperfine interaction. When we talk about that, that is the interaction between the nuclear magnetic moment and the spin or orbital currents due to surrounding electrons. That is given by hyperfine field is given by dipolar, orbital and a Fermi contact interaction. The first one is due to the interaction between the nuclear magnetic moment and the spins outside the nucleus. That is what we call it as dipolar interaction. That's usually here when we take up some of the examples, we will pay attention. about that spin density of the d shells at the same atom. Usually, the interaction between nuclear magnetic moment and d shell electrons is corresponding to dipolar interaction. The orbital field terms arises from the non-quenched orbital moments of the valence electrons, and the Fermi contact is another important one, and that Fermi contact interaction again subdivided into 3 more units. What are those 3 more units? The first one is the first term corresponding to cold polarization. That happens due to exchange interaction of the inner s electron with the on-site magnetic moment of the 3d electrons. Okay, there is a core polarization happens between the inner s electrons and 3d electrons. The second term arises due to spin polarization of the conduction electrons with the on-site magnetic moment of the nucleus itself. This is basically due to conduction electrons. And the polarized d orbitals of directly neighboring atoms hybridize with the valence s electrons, leading to polarization of the valence s electrons. This polarization contributes to the hyperfine field, which referred as transferred hyperfine field. Okay, this is corresponding to the third parameter. Just for the whoever wants to read it out, let them understand. That's why the entire description is given here. And again, these fields would contribute to the magnetic field approximately to these values as given here. Okay, 7 Tesla, approximately 7 Tesla for nickel, for iron 33 Tesla, and for cobalt 21 Tesla. Please pay attention here, because this internal field NMR, when we talk about that, the design of the experimental setup, we cannot use a ready setup for studying these individual nuclei, because in any other material, we can decide what should be the operating frequency and what should be the incident radiation frequency to observe NMR. But here we have to, that what I mean to say is that in commercial NMR spectrometer, the frequency is up to, in the sense, the selection of frequency are depending on the strength of the external magnetic field. Okay, we can tune or we can make measurements at whatever the frequency we want in commercial NMR spectrometer or any other conventional NMR spectrometer. But in internal field or zero field NMR, we have to make our electronics to suit to that particular frequency or particular sample what we are planning to study. Therefore, to make these measurements to happen, we need to have strong hold on the electronics, and we need to design our electronics to suit to measure NMR at corresponding to these frequency, these magnetic field. Correspondingly, there will be a change in the frequency also. There are advantages and disadvantages. Only advantage here is we don't need to have very expensive superconducting magnet to perform these experiments. But disadvantage is that we should be strong enough in the electronics to fine tune our spectrometer to match with this particular magnetic field, that mean to say in terms of frequency. And let us try to, this is already known thing, that's why I just read it out. Ferromagnetic materials contain magnetic domains, and this magnetization within each domain points in uniform direction. But these magnetizations of the different domains may point in different direction. Therefore, the reason separating these domains, wherever we are having individual orientation, we call that as domain wall. Okay, the domain and domain wall enhances the signal intensity. This is the crucial part in internal field. Though external magnetic field is applied to the system, and we know that NMR is very less sensitive signal, very weak number of atoms would contribute to the NMR signal. Therefore, somehow we need to make that enhancement. Unless RF enhancement happens within the system, okay, we cannot make any observable NMR. In the sense, we cannot make NMR measurements. Therefore, we need to understand how this RF enhancement happens within the system. Therefore, let me read out this domain enhancement, how it happens in the domain. Okay, applied radio frequency tilts easy axis of magnetization, which in turn tilts the hyperfine field. And this greatly enhances the effective time-dependent field at the nucleus oscillating at the RF, with consequent increase in the detection sensitivity due to the increased probability of making the transition. Basically, what happens, though we are applying particular amount of radio frequency to the system, we need to, why ferromagnetic systems are very essential, and the presence of this domain and domain walls are present. These domains make this RF enhancement to happen within the system. That is, in the domain enhancement, in domain wall, what happens when RF field rotates the domain walls, which results in very large time-dependent change in the magnetization at the nucleus. And these domain walls will peak at a particular point where spatial rate of change of magnetization is greatest. This result in enhanced RF field, which increases the transition probability about 2 times when compared to domains. What happens is that whenever we are trying to study these magnetic systems, this enhancement is the parameter which should happen for us to observe internal field NMR signal. Okay, that happens when we have these domains and domain walls. Okay, and sometimes why we are targeting or why we are emphasizing these finer aspects is that, again, this nickel and some of the nuclei, we may not be able to make effective measurement because of this, because of the absence of this RF enhancement. Okay, and again, same thing we have applied here. RF enhancement arises because of the inherent property of the ferromagnetic materials due to the existence of domains and domain walls. And this applied RF field induces oscillations in the electronic movements of the ferromagnetic material. And these oscillations lead to change in the hyperfine field due to the coupling via hyperfine interaction, resulting in the RF component of the RF field. This resultant RF field is due to it is the sum of applied RF field and induced RF field at the site, which give rise to major change, so that the usual home-built spectrometers also will be able to detect the signal. And just for the completeness sake, whatever we in the earlier slides, we only talked about the hyperfine field or strength of the magnetic field in terms of Tesla, 33 Tesla. For iron systems, nickel, 6.5 Tesla. Therefore, the corresponding NMR frequencies, what we observe, will be in the order of 26 to 28 megahertz for nickel system. For iron, we need to have 45 to 47 megahertz. And for alloys, iron, cobalt, okay, the frequency range would vary from 200 to 300 megahertz. And for manganites, it could vary from 300 to 700 megahertz. The bottom line here, what we are trying to explain here is that whenever we design a zero field magnetic, say an NMR spectrometer, we need to make sure that our apparatus can work from 20 megahertz to at least 400, 500 megahertz. Therefore, there is a reasonable commitment is required for us to make our electronics strong enough to make all these systems to be studied. Now we will consider a cobalt. What we did, we synthesized the cobalt, and depending on our experimental conditions, it formed cubic phase as well as hexagonal close packing phase. And when we measured NMR, zero field NMR, as a function of frequency, then we did not see only one peak, we saw different peaks. And this is sort of, as you can see, that this is the raw data, what we have plotted here. And we took bulk cobalt also, which is commercially available, and we synthesized cobalt in 2-3 methods, and we got spectrum like this. And the beauty of this zero field NMR is that by analyzing the spectrum, we can always estimate which portion, in the sense, whenever we are considering FCC domain wall will give one particular NMR signal, and domains themselves give another particular NMR signal, in the sense at another particular frequency. And same thing happens with hexagonal close packing also. And what I mean to say is that by making measurements using internal field NMRs spectrometer, we can identify contributions from the domains and domain walls, and also whenever we are having two phases in the system. This kind of complete, what we can say that complete picture of this entire phase composition also one can estimate using internal field NMR spectrometer. And in this particular example, we measured, and when we synthesized the compound, we could not get complete hexagonal phase also, and only FCC. In one of the methods, we got FCC structure. When we followed another method, those details are given in the reference what we have mentioned, and we got another signal at HCP. 1 minute. Okay, and then we were able to get cobalt FCC gives magnetic, in the sense the corresponding frequency was, there was a difference of 7.4 megahertz, in the sense when we plotted in the, as it is given here, the difference between this peak at 212 megahertz and another one is 225 megahertz. Okay, it is around 6 to 7 megahertz difference between one phase, that is FCC phase, to the HCP phase. Therefore, using IFNMR, we can easily, we were able to detect this signal explicitly, and we are able to identify domains and domain wall contributions also. And that just to give some more details how this XRD and SEM we can correlate, and we got, when we prepared the compound with ethanol as a solvent, we got HCP phase, and when we used water as a solvent, whenever we synthesized the compound, we got it FCC and HCP phase, and the commercial cobalt was having only FCC phase. Okay, and here though we claim that it is completely HCP was predominant, and only small portion of FCC was still present here. And why I have given this slide, XRD slide, is that by looking at that, the problem with FCC phase and HCP phase is that there are two peaks. One is 220 peak and 110 peak. Okay, for both FCC and HCP, I have two peaks here, same peaks. By whenever I make measurement here, if I get one peak here, I cannot make a conclusion that since one peak is coming, whether it is due to HCP phase or FCC phase, it is hard to identify. Only through our NMR, we were able to identify the composition or how much percentage of HCP was present in the system. That we were not able to make it using XRD. Therefore, in that way, IFNMR plays major role in identifying this phase composition compared to XRD. And same experiment we have explained in detail here, and different compositions, how domain walls and domains can contribute. We have explained in detail. Let us skip for time being. And when we quantify whatever the observables we had it, okay. Sorry. And we were able to identify what is the area corresponding to that peaks, and we were able to identify what is the portion of FCC when we prepared with water, P and See, when we prepared with ethanol as a solvent, we were getting more composition in the sense our compound formed in HCP phase as given in this phase composition 40 plus 30. There was 75% of the compound was following HCP phase, but in the case of water, more composition in the sense we had equal contribution from HCP phase as well as FCC phase. And these are the conclusions. Okay, cobalt at C, that is in ethanol as a solvent, we got major HCP phase to the bottom line. Okay, and these are the next systems. What we are considering is ferromagnetic ceramic insulators. We have considered the spinel ferrites, and spinel ferrites usually we write it in this form: metal, iron oxides. Okay, that could be zinc ferrites, cadmium ferrites, or inverse spinel ferrites, nickel ferrites, or cobalt ferrites. And these ferrite systems also we will be able to make measurements using internal field NMR. We'll take one example. We took nickel cadmium ferrite and we kept on changing the composition. In the sense, we kept on replacing nickel by cadmium, and as we started doing that, at the composition X corresponding to 4, okay, then the compound changed from inverse spinel to normal spinel structure. This we got it from Rayfield analysis, and VSM measurements did not really, we were not able to explicitly make that statement, as you can see that this NCF3 corresponding to this highest magnetization, we were able to qualitatively, we were able to see that. But when we performed zero field NMR experiments for the same series of compounds, we could see that when we started with nickel ferrite, okay, we were able to see two different peaks corresponding to two positions. Okay, one is as we have mentioned here. Okay, and there are two sites corresponding to A site and B site, and we were able to get two independent peaks for nickel ferrite. When we kept on adding cadmium to the system, then what happened? These two peaks start merging with each other. And up to this point, they started merging with each other. And at NCF4, we got only one peak, which is broadened and which extended up to 75 megahertz. Okay, the area under the peak is proportional to the iron content at that site, and substitution of cadmium results in the shifting of the iron ions from A site to B site, which result in decrease in the iron content at A site. We'll give this A site and B site is familiar to us. Okay, and these are the finer details of this site distribution. What I mean to say is that from this zero field NMR, we can estimate how many iron ions are in the A site or in the B site. That we were able to do that. That is the bottom line here. I am not spending much time, and this is just for the inspiration purpose. This is the starting point for our group, where we are trying to understand, do zero field NMR for thin films also. We have not done any experiments in our labs so far. Okay, with that, I would like to conclude my topic with these summary points. The deuterium NMR demonstrates short distances, and for biological applications, the physical properties of the biological samples we can study, because our lipid molecule behaves like a liquid crystal, and all liquid crystal theories can be understood better and can be correlated to the drug industry applications. Therefore, and at the same time, these undulation forces and protrusion forces can be distinguished using solid state deuterium NMR, and using proton and fluorine NMR studies, we were able to identify the phase transitions and quantum rotation tunneling. And using zero field NMR, we were able to there are a couple of applications advantages we have in zero field NMR. One is the phase coherence or phase contributions we are able to identify, and it is a very good analogous tool with respect to mass bar spectroscopy. And also we are able to identify in the recent upcoming paper, we are able to identify or correlate zero field NMR measurements with respect to Raman spectroscopy results also, that I have not presented today. And with that, I would like to acknowledge my group of people and collaborators, of course, with Professor K.P. Ramesh from Indian Institute of Science and Professor Ramkrishna Damble from Bangalore University, and my collaborators in US institutions, Michael Brown from University of Arizona and Horia Patrake, Professor Horia from Indiana University, Purdue University, Tallahassee, from US, and Professor Rana Ashkar. We recently started doing some experiments with them for neutron scattering and molecular dynamic simulation experiments. Those we did not explicitly mention in this talk. And George Keshavali from Yale Cornell Medical College, and our earlier collaborator, now he is working in Oak Ridge National Laboratory, Dr. Jacob Kiran. And also I am thankful to the organizers. I am ready to take questions now.
Thank you, sir. Thank you very much for that wonderful presentation. And in fact, we have received so much compliments from the participant sides in YouTube stream. And along with compliments, we have received some questions.
Yes.
To raise. And as it's a matter of time, I will just put 2-3 questions in front of you.
Yes.
So that
please.
Participants will get benefited out of it. So the very first question from a participant by the name Dr. P. Selvi Vallavan.
Okay.
Sir asks, is NMR possible for rhizobial or bacterial image processing?
Exact terminology what he is using, I may not be available, but bacterial image processing.
He says rhizobial.
Rhizobial, that's why. The technical word, I am not familiar with that.
And but along with mentioned bacterial image processing.
Yes, bacterial image, the only thing is whenever we go with image processing, we go for large molecule. Okay, and whether we are able to make that bacterial particle to be at rest whenever we make transitions or whenever we record the spectrum, that I am not an MRI expert here, therefore it should be possible, but the technical difficulties I am not aware of that. But it is possible to record the image. What are the other problems which could come in? I am not aware of it.
Sir, one more question we have.
Yes.
Can you elaborate a little more on quantum rotational tunneling?
Yes.
One participant by name Murali Krishnan is asking this question.
Yes, I will try to show this particular relevant graph, and then I will try to explain that.
Yes.
1 minute. Okay. Here, actually that one particular slide, I did not show it. Here, basically what happens in this particular spectrum, what happens, why this spin lattice relaxation time is going up is because whenever thermal motion is happening, okay, whenever reorientation of a methyl group is happening, whenever we decrease the temperature of the system, our thermal energy is not sufficient to make this methyl group to move from one equivalent position to the other equivalent position. That freezes as we decrease the temperature of the system, because that motion occurs because of the thermal energy supplied to the system. what happens when we bring the temperature down, then hypothetically or classically, we cannot expect the particle to reorient from one equivalent position to another equivalent position. Then, but when we make measurements, for example, here around less than 100 Kelvin also, when we make measurements, we do see whatever the minimum we are seeing at the high temperature, similar trend we observe at low temperature also. Then how come? How well molecule is going from one equilibrium configuration to the other equilibrium configuration? How does it happen? It is very much similar to our tunneling process. Okay, unless you are giving sufficient energy for an electron to jump to another potential well, it penetrates through the barrier. That the same concept happens here also. This methyl goes from one reorientation to another reorientation without jumping over the potential height. That we call it as quantum rotational tunneling. I think I have answered to Professor.
Thank you so much, sir. And I have one last question.
Yeah, please.
And once again, that is from participant. Is there any experimental proof that the internal field in bulk iron is 33 Tesla? So you have mentioned in one slide.
Yes. Yes. Bulk iron. Did I mention iron over there?
You mentioned it 33 Tesla.
Yes, that is very well because we ourselves have performed several experiments. Okay, in the sense probably he might be asking that how did they measure this 33 Tesla?
Particular technique maybe is asking.
Yeah, in the sense this is experimentally we are performing the experiment. In the sense we perform this zero field NMR experiments. Most of our papers, 2-3 papers are on that iron NMR. Okay, if he is asking me why I am not seeing outside, if that is the question, answer will be different. But it is we have many papers on this iron which gives 33 Tesla. Why we are not seeing it outside is another question. If his interest is to understand that, because this whatever 33 Tesla I am talking about, that is happening at the site of the nucleus, not outside. If I take iron rod and keep it here, why I am not seeing 33 Tesla? If it is his sort of common sense type of question, then obviously because this 33 Tesla is occurring or the 33 Tesla is felt at the site of the nucleus, not outside. That's why we don't see it. But the 33 Tesla, it is well established technique. We ourselves have performed experiments on that. I hope if he wants to have the clarification I can give.
Yes. Thank you so much, sir. And I once again thank you for being part of our faculty development program and for delivering and sharing your knowledge with our huge number of participants. And thank you so much, sir. And
thank you.
Chandra.
Thank you. Thanks for the opportunity.
Thank you very much for your wonderful presentation on study of nanomaterials for biological and material science applications, solid state in NMR perspective. Thank you very much, sir.
Thank you. Thank you all for your patience. Thank you.
Thank you, sir. Thank you, sir. From Department of Physics, I thank you again. I'm Dr. Duraswamy, head of the department. Thank you, sir.
Bye, sir. Thank you. Thank you very much. Bye.
Dear participants, tomorrow the session will start at 9:30. The first session will be delivered by Dr. G. Paramesh from Prashanti Nilayam. He will be speaking on glassy state of matter, experimental studies on understanding the glassy state. The session in the second session, Dr. B. Sridhar is from Hyderabad and he will be speaking on single mode multi-component solid state forms. The feedback link will be open till 2:15. All participants are requested to do fill the feedback before 2:15. Thank you. Good day.